morning, everybody. I'm really surprised with the amount of people coming here. So let's start with checking out if everybody's in the right room. Who knows what OpenMP is? That's a good score. Who has used it before? Who wants to use it? Who hates to use it? Even the, okay, good. Let's see if we can reconvince you. Okay, does this sound familiar? I hear a few people laughing, so probably it is. But isn't this the usual problem you're fighting when you're doing multi-threaded programming? It sometimes works thanks to something called Eisenbugs, which you don't see if you look at it, and they do appear when you're not looking. So let's try to avoid those race conditions by actually making correct code. And then we introduce OpenMP. Okay, this is me. I have some kind of a dangerous hobby in trying to fly without an engine. And other than that, well, I work for a company who is focusing on doing multi-core programming. So we do training, we do consultancy, and we have a tool to actually take source code, analyze its operation, and work with you to together make it parallel. But of course, I'm not here to make an advertisement, so let's do a small deep dive into OpenMP. If you want to do proper software optimization, you can do that at 3 different levels. You can do it at the top algorithm level, which is what all those scientific guys are doing. Are those scientific guys in the room, by the way? Everybody else is a programmer? Okay, so about half of the room are neither. Okay, cool. Sysadmins? Yes, a few? Okay. So the second, once you have the best algorithm you can find, you need to find the best coder you can find, so you get the best C code. And that's where a lot of work can be spent using OpenMP to get it as optimal as possible, to make as much use of the hardware resources you have. And only then start worrying about that third level, getting to the best assembly code, the best machine code you can. Of course, anyone writing an HPC program in Python is still in that third option out of the box. But it's an important step. Compilers tend not to write optimal code, but tend to do a reasonable job at it. So you need to help them to get to the best level. Again, something OpenMP can help. So what is OpenMP? Apparently everybody already knew. So yeah, it's this. It has been around for a while already. Of course, even more people. It originally started out when different vendors realized, hey, we need some kind of a paradigm to attack those multi-core systems that slowly start appearing. Almost at the same time, multi-core systems started disappearing again. So OpenMP went in a limbo for a while. And by the end of the 90s, it researched. People also started getting interested in C, and by now OpenMP 4 is mostly talking about C and does Fortran on the side. Support for OpenMP is still catching up, especially on the Microsoft front. It's still lacking at that. And as of about a year ago, even the people using Clang start becoming happy because OpenMP is coming to Clang. Finally, code. It took me 15 slides to get to code. Oops. OpenMP is, for now I'm going to show most of my examples using GCC. Only in the end I will talk a little bit about the intercompiler. In both cases, you use -f OpenMP in order to say, hey, dear compiler, I want to compile with OpenMP enabled. At that point, the compiler will understand that you have a -pragma OMP. One very important paradigm of OpenMP, dating back to the C standard, if you see a pragma that you don't understand, you ignore it. Which means that this code should be the same if you compile it with OpenMP or without. Unfortunately, there are two examples in this entire tutorial set that do not adhere to that principle. This is why. Because if you ignore the pragma, you would only get one printf statement, and if you compile with OpenMP, you get 4. So that's not the same, so technically this is an illegal OpenMP program. Okay? So, once you compiled it, so we have an include file, we have different number of function calls to actually get things like get a number of threads, get my thread number. Thread number starts counting at 0. That's why we get 4 threads, and as usual, they do not appear nicely in order. If there's anyone still surprised that they do not appear in order, we need to talk. So, OpenMP is meant to be used incrementally. You start with working code, sequential working code, only then you start applying OpenMP pragmas. Which means that you always can check back whether your code still works as it should. And the second advantage is that you always have that sequential algorithm available, so your scientist can walk back, think a little bit more about some optimization without screwing over everything. Let's make it slightly more complicated. Now I only have a pragma in the middle, so we start sequential. There's only one thread. Then we go to a parallel team. So each thread of the team will execute printf. And as you can tell, there are now 4 threads in my team, and yet another in order. Once this block is done, so this pragma only applies to the next code block, which is in this case 1 line. The team goes back to sleep. I only have 1 thread left, so that's why I have 1 thread in the end. Well, nobody looks surprised. That's good. There are several work sharing constructs in OpenMP. The easiest one conceptually is OpenMP single. At least in Scope it's simple. Essentially it means there's only one thread executing what is in between. The hard part is figuring out which thread. And what are the others doing at the same time. So I'm going to ignore that for now, but that's where the problem with OMP single is. OMP sections and OMP4 I will discuss very soon. All 3 say something about the next piece of code, how threads will operate with that next piece of code. Let's go to OMP parallels. Sorry, OMP sections. First you annotate, okay, I'm going to have a block with sections in it, and essentially we define 3 sections, which are run in parallel by 3 different threads. Will it hold? So, if you have 4 threads, that means that 1 thread is still idling in this code, and the other 3 threads in parallel will initialize by matrices. And after the sections is done, I still have 1 thread that will do some computation with the entry of the matrix. Really feeling scared here. Sounds good, does it? Unfortunately, you are working with multiple threads, you will face at some point the situation where you have threads that need local data, that need data that is not shared. We'll see quite a few examples further down in the slides. But you need to start paying attention to which memory is allocated where. Especially if you are on NUMA systems, that is getting really hairy, but I don't want to talk about that in just a tutorial. So for now, let's assume we have a flat memory system. All the memory is at the same cost accessible by all processors. Still, we need to worry about what variables are private to a thread and what variables are not private to a thread. So that's why OpenMP introduces different concepts to identify, for example, if I say default none, none of the variables allocated available so far will be visible to my thread. Well, that's not really useful. So that's when you can say, okay, I want a variable shared. I can read from it. Whatever I write to it will be visible to all other threads. That's all correct. I can say I want the variable first private. The original value this variable has comes in. I can use it, and whatever I do with it goes away when I end my task. So if you have 4 threads that each have a first private on a variable, all 4 will work with the initial value, and all 4 will discard the value afterwards. Last private is exactly the opposite. The variable does exist, does not get an initialization, and the result will be copied out. So if you have 4 threads having the same variable as last private, the inverse approach. Let's try to put this into use. So this is the default. I put a shared here, which really doesn't make much sense because shared is the implied default. So let's make it harder. I still have my 3 matrix pointers. I'm still going to initialize them, but now I have a shared here, a first private here, and a last private there. What is my outcome? Let's start with M3. Is the bump going bigger? Okay, M3. Who dares? What happens to M3? Yes? So the M3 end result is copied out. There's only one M3, so we're happy. M2.
It's not the alpha, the line 7, I guess.
Yes, so M2 is initialized?
No. No? Yeah, we get garbage from the line 1, but shouldn't be a problem, I guess. So, yeah.
You're close. Anyone else want to make it more specific? Excuse me? Yes. So all the effort is spent to initialize M2, and the result, poof, goes away. M1? You've been already. Sorry. No, not you. Not you. Anyone else?
It depends which thread is processed first.
Okay, explain.
Because it's shared in the first thread, but it's also exported in the last thread. So it's which one closest latest. But there's 2 initializing in the last thread, so hopefully that's one that ends like latest. So I would guess the last thread.
I wouldn't dare to make that guess. You're very likely right, but I wouldn't bet my life on it.
No, me neither. But
So, indeed, M1 is initialized twice. No, a local copy of M1 is initialized twice. In one case, the local copy is the shared copy. In one case, the local copy is actually copied over. Because we're talking about a pointer, we probably, note, probably, will wind up with a valid pointer in the end. Again, no guarantees here. So always use default none when you start coding to actually make sure that all variables are initialized like you expect. And once you get to the stage that everything works as expected, I suggest to keep it there. So if your scientific guy comes around and starts messing with the code, or your dear co-worker who understands less than you do, all of you have one, right? Or your boss comes around, the default none will prevent him, her from screwing up. And of course, I'm going to not use default up. Yes?
Maybe a question with the previous code. With the initialization of M1 and M2, I'm not sure, but aren't we going to have memory leaks if we are doing some dynamic variable? What happens to the first initialized M1 and what happens to the uselessly initialized M2? Are they local, even if dynamically allocated, or does it pollute the memory space?
I love the question, thank you. Who dares to answer that question? What happens to M2, the initialized M2?
Well, it really depends what this initialized matrix does. If it returns pointer to some buffer or whatever, or if it makes malloc and allocates memory.
Well, I would guess that matrix is some kind of a pointer to something. And then the big question is it a shared pointer or is it just a pure C pointer? If it's a shared pointer, you may actually get away without a memory leak. Usually, this is just a big memory leak because, yes, initialized matrix will have malloc something, will have filled it up, and the pointer is just thrown away.
Okay, so.
And C doesn't do garbage collection.
Thanks.
Love this kind of questions though. Keep them going.
Is the performance tunnel really for leaving just default none as in code? I wouldn't expect.
Not that I'm aware of. So I don't expect very much penalty. The only thing you do is actually make it more straight. The codes that you generate should be the same. Well, I guess everybody's seen an example of this style before when you start talking about parallelization. So just some dump matrix multiplication, let's multiply M1 with M2 and put the result in the rest. How many ways can we parallelize it? Well, quite a few. Shall we go for 3? Let's take the smart one first. Which one is the smartest to parallelize? 4? Oh, you mean line 4? No, the 4 loops. Absolutely. So, 4 loops. Sounds like a good plan. Which 4 loop makes most sense to parallelize? Can somebody speak up a little bit because I'm a bit deaf? Line 8. So if you make this one parallel, we will do that. But it's probably the least performance one because you will constantly start the team, stop the team, get in line 8 again, start the team again. They will do a little bit of parallel computation, stop the team again, go away. So it is important that you want to parallelize. If you start parallelizing loops, take the highest loop you can find. Because the highest loop you can find has the most body, the most time it's spent in an iteration. So the starting and stopping time of a thread has less impact on the overall compute time. Make sense? Okay. Part of how OpenMP works is that it adheres to something called the for join pattern. So every time you hit a parallel for, which will be in the next slide, at that point the threads will be created or woken up. They will perform all the iterations of the for in parallel. Once the iterations are done, the threads are put to sleep, put in a thread pool, whatever. At least they stop working for me. Only one thread continues until it hits the next point. Make sense? So this way, the programmer still has his sequential behavior. There's no thread going astray doing weird stuff. No, you have still your sequential behavior, but you take the performance, you spread it over more threads when you can. So let's parallelize the top one, because it has the most body. So I throw in a parallel for. That's nice. So that means that this for, it will take all the rows and start spreading them up. Okay, the first set of rows goes to thread 1, the second set of rows goes to thread 2, etc., etc. How the split up of the rows across the threads is done will be the next slide. But wait a minute, there's a private call and a private K there. Why would I need those? Yeah. So I need to make call private because every thread needs its own copy of call, or they will start messing with each other. Agreed. The same is true for K. And of course, if you're programming C99, you could have just said for int call here, and you wouldn't have needed to do this. But if you're stuck with your boss specifying kerning and Richie C, this is what you have to do. Okay, so we're going to use private when needed. If you are the lucky bastard, you can use C++. Instead of kerning and Richie C. At least you'll be happy to see that OpenMP allows for STL iterators. I haven't seen any OpenMP statement about the range operators in C++11 yet. I would expect that it's in there, but I haven't checked. One thing we'll jump on in a minute, no branching in and out of the loop. No breaks, no continues, no exceptions. If you're C++. The reason for not doing that is obviously that you add a logic problem to your code if you have an early exit. Because if you have this amount of work done, you start sequentially and you go this way and you exit here, you know where you exit. If you have this amount of data and you split it up and you exit here, where was that thread? Where was that thread? So you have no clue what the status is of everything else you processed underneath. So from a logic point of view, introducing an early exit or a cancel, like it is now called in OpenMP4, usually doesn't make sense unless you really know what you're doing. So that means you have to understand the code you work in. So I have my big set of iterations that I'm going to spread over. If I take a dynamic schedule, I'll have the first 4 go to 4 different threads, the second 4 go to the same threads. So thread 1 will take 1, it will take 5, it will take 9, etc., etc. Thread 2 will take 2, 6, 10, where the static schedule will say, okay, 1 to 100 go to thread 1, 101 to 200 go to thread 2, etc. Why do you need to have the choice between the two? Why are both valid choices for some situations and not valid choices for every situation? Excuse me? NUMA definitely has an impact on this, but it's not the answer I'm looking for. Because that's a low-level answer. You're right. It has impact in some cases, but there's a much more obvious reason why this sometimes makes sense.
Depends on the runtime of the jobs.
Yes.
I know the runtime of the job and the runtime is all jobs that can be
Yes.
Otherwise, I think dynamic.
Absolutely correct. That point. So, this is indeed a problem of load balancing. If I have a series of jobs and every next iteration takes longer to compute, say prime numbers, it would be really bad if thread 1 takes the 100 easiest ones and thread 4 takes the 100 slowest ones, because that means that, well, that's a bit unequal. So at that point you want to have them jump over each other, a round-robin schedule, to make sure that they try to spread it as nicely as possible. If you have an equal load across every iteration, the static schedule probably fits closer to what you expect. As soon as you start putting cache behavior, locality of memory into play, things get significantly hairier, which is beyond what I want to talk about today. If you need that, go get this. So, I do want to do this in order. Let's put the pragma parallel 4 on that inner loop. And just so to keep people in mind that we're sharing all variables that were declared before, I made explicit and put shared temp there. What would fail? Nobody? Everybody would happily use this code. Yes? Okay. Do you know the name for this pattern? Okay, doing it wrong is a good one. Anyone else? Yes? Okay. So what you're referring to is called the reduction. We'll get to that. I'm going to bench K for a few seconds. We'll get back to K. Anyone else? This is multiple threads writing to a value before they actually read to it. So this is an empty dependency. Doesn't ring a bell? Okay, sorry. So K. Let's quickly discuss K. OpenMP is smart enough to understand that if there's a variable mentioned in a for statement, that variable is called an induction variable and will automatically be split up across the different threads. Each thread will get its local copy, each thread will understand how to get to the different iteration. So K is not an issue here. TMP indeed gets written to by every thread, gets read from by every thread, so the end result will be likely very ugly. There's two ways to solve this. Depending on the underlying code, either can be correct, but in this case, let's not use this suggestion. Because what we can do is we can say, okay, we make all the writes to TMP atomic, which means that we know for sure thanks to underlying mechanisms in the processor, and mostly the cache mechanism of the processor, that every write will succeed. So I will read the value, add to it, write it, and I'm pretty sure that no one else will be in between this read, modify, write action. That's what atomic promises. The disadvantage of using atomic is that as long as the thread holds that cache line where the TMP variable is for itself, no one else can claim it, no one else can write to it, so all other threads have to wait. Especially if you are in such a small loop like this one, essentially you're kind of sequentializing your code again. However, if you would have TMP as an array, for example, because you're doing some kind of histogram calculation, atomic may be the best way to go forward. Maybe. No. Thanks for asking. So, the question is an atomic a mutex? The answer is a very big no. It's actually the reverse, but I'll get to that. What is important is that an atomic is on cache level, very down in the processor, where if the processor writes to memory, well, reads from memory, modifies, writes to memory, it will say, okay, that position is for me, nobody is allowed to touch it in between. So we're talking about holding that line for 4 or 5 cycles. Going up to a mutex, the mutex says, okay, if I claim this mutex, which is variable, no one else is allowed to claim that variable while I hold it. So anyone who claims that, wants to claim the variable while I hold it, will be put to sleep. That's at least 1,000 cycles, and will only be woken up when I actually let go of my mutex. Waking up a thread and getting it to run is probably another 2,000 cycles. So 3,000 cycles versus 5 cycles. There's a very big difference in the number of cycles. Atomics should work on any cache coherent system, because that's one of the requirements to be cache coherent. Can I complete my mutex versus atomic story? The only way to write the mutex is using atomics. Just to put them into perspective. There were 3 different. I'm essentially sequentializing the code again. So yes, I will have 4 threads who all have to wait at cache level before they can read, modify, write this variable.
What happens if I use a 64-bit variable and my CPU architecture doesn't support 64 bits or only 2 bits?
So what happens if you have, well, let's make it slightly broader. What happens if you have an atomic operation done on a structure that your processor cannot handle atomically in assembly code? So, for example, if you use this in C++11, where you can say for any random type, you can say, okay, make this type atomic. C++11 would add mutexes underneath to protect all accesses. Let's describe C++ again. If you do this in OpenMP, I bet you get a compiler error. I've never tried it actually, but it makes sense that at some point it will warn, hey, I'm trying to write something which I cannot do in a single operation. And then we're back to different architectures have different responsibilities. In ARM, no, I didn't put the slide in, sorry. In ARM what you see is if you do an atomic write, it will be essentially a load exclusive. So give me that cache line, give me the value in the cache line. That cache line is now mine. I write to it what I need to write, and at the end I check whether the cache line is still mine or whether somebody else stole it away. if somebody else stole it away, I'm going to redo my operation. If you go to a 64-bit, so if you go to a larger structure, essentially this load exclusive and store exclusive get further away, which means that probably the test whether you still had it exclusive after the last write will fail more often, so you have to redo it again. That's all. But that's in ARM, so you can solve this. It probably will be solved by, well, having to wait a few more times before it gets right. If you go to Intel, I believe there is no problem, because even on a 32-bit you could already score 64-bit. So, spin longs, you're feeding on one of my pet peeves. Spin locks don't work. Let's take this offline because I only have 20 more minutes left. I wouldn't try to do this with spin locks. There's, oh, yes, one more. Can you start again? Yes.
So if I was to put shared 10 and then some other variable, then if on the following line I reference the number that reaching up to how does atomic know which variables are atomic?
Thank you. So let's make the question slightly simpler. Atomic means read, modify, write, all joined together. What happens if I have multiple writes in a single sentence? Or what if I have multiple reads and then do a write? What happens? If you are stuck with OpenMP 3 or below, you are in bad shape because it wasn't specified in the system. Only in OpenMP 3.1 they added clauses to specifically be able to tell, take that write or take that read or merge this and not that. So the R to OpenMP atomic, there are clauses to specify closer behavior in case where people might start getting confused. That's why I love the question. I was going to ignore that just because there's so much to tell. But there are more clauses to OpenMP atomic that will help you out in this kind of cases. There's the reduction. OpenMP does have a specific trick to do this better, where essentially you specify, okay, I see a reduction expression in my loop. The reduction expression means that there is a variable that sees an operation, sees it in every iteration, it uses data, and all of the data and the operations can be interchanged. So in this case, I specify operation plus on variable TMP as being the reduction. So addition is, except when you're talking floating point, addition is something where you can change the operators here, right? Okay, I threw the next slide out. There are different types of operators that, yes?
I would expect less performance not on parallel computing, but on some kind of vectorization. So some pipelining.
We'll get there.
Okay.
And yes, I agree. And the requirement for n is actually here. So if you have an OP parallel 4, the requirement for this clause is that it has to be known prior for entering the for loop. So that was the original requirement, but it's no longer the requirement. So the requirement now is you need to be able to predict at the start of the for loop, you need to predict the end number, and it is not allowed to change during the for loop. So instead of the plus operator, you are also allowed to use a few other operators like multiply, minimum, maximum, store into an unordered list. Things like that are all reductions. Starting with OpenMP4, you can even declare your own function as being a reduction. Quite a bit hairy syntax, but you can make your own reduction functions. I'm quickly going to jump over a few other tricks, and then we're going to see a little bit more code. I already discussed OP single. So what if you have a very expensive compute function that you want to split across multiple threads, and you can do so. So you have a team of threads attacking that compute. Then you have one operation that needs to be done by just a single thread because there's no way you can parallelize that code. So you can say, okay, on P single, only one thread will run that code, and only when that thread is completed, all other threads will continue. So that's important to realize that there is a barrier at the end of OP single. All threads need to be there or no one continues. OP barrier here is needed to make sure that all threads are done before we actually start doing the reshuffle. Otherwise we start reshuffling data that may not be complete yet.
It's like a charm.
Essentially no, because the threads, a barrier will keep all the threads alive, where a join will make them put to sleep. So if a barrier immediately is followed by another for, none of the threads will be put to sleep, and all of the threads will immediately share the workload of the for and continue. Another nice construct, especially if you start working with recursive code, is using task. Essentially like a remote procedure call. You can say, okay, I have this amount of work that needs to be done by somebody else. I don't care when you do it as long as the result is ready at some point. So in this case, we have a list reversal, where for each element in the list, we hand out the job to some task. All the tasks will be put into some kind of queue, and all other threads in the team will empty that queue and do the processing. If you, by accident, have code where the ordering needs to be kept intact, yes, you can. There is an OpenMP for ordered, where if you announce it up front, OpenMP can introduce enough code to make sure that the results can be printed in the same order they originally were. There are a few requirements here, like there's only one order to be allowed in a single thread, single for loop. Don't expect magic performance here, because this takes a lot of synchronization underneath within OpenMP, so you will hand out performance. If you can get rid of that ordered requirement, you can get 4x likely on an algorithm. If you have ordered in there, you are lucky if you get 2.5. Yes. Okay, sorry, smile. And I hadn't expected to see so many people, so my boss will be happy. Smile. Oops. Sorry, need to do that again. Yes. Smile in the middle. Smile on the right. Yes. Thank you. So at least I can prove to my boss that, yeah, it makes sense to come here. After all, he's paying for my hotel room. Okay, back to the topic. Something that we ran into quite a few times when we started toying with tasks is that you probably want to only parallelize, so fork off a task or paralyze for loop if there's enough work to actually do so. Because waking up the team, putting the team back to sleep takes time, thousands of cycles. So if you can make a decision whether you want to start a team or not, that's convenient. And OpenMP has I think 3.0 has a clause to actually say, okay, I only want to do this in certain cases and keep as a single thread otherwise. Then we have a few other directives, or actually none of these are directives. No wait is a clause that you add to, for example, a single to indicate that all the other threads that are not busy can continue. So you can, this is improving parallelism in some cases. Critical is a critical section. So you can identify this piece of code, only one thread is allowed to be there at the same time. All the threads that enter this come at the beginning of the critical have to go through, but only one is allowed at the same time. That's very different from a single, right? Because a single says only one thread goes through it, the rest jumps over. There's also a clause master, which identifies, okay, all threads that enter it, only the master is allowed to continue, and everybody else will jump to the end and continue afterwards. Immediately. They don't wait. Flush. If you have two threads, and I'm first this thread, and I'm going to write to 3 different variables, the compiler is allowed to reorder in which order I write to the variables, because essentially from a C point of view, I can't tell in which order the variables were written in the first place. I only know after the first, all 3 have been written. Imagine that the last one you write is a flag, and that flag is read by another thread, and only when it sees the flag change, it knows that everything is written and it continues. If your compiler starts reordering, or if your processor starts reordering, those writes may not be in order. The flag may actually be written first, and only at that point means that the other thread already starts working, starts reading those variables that haven't been written yet, so you get the old values. That's the type of case. This is, first of all, this concept, memory reordering, is the cause of a lot of very, very, very subtle bugs. It will work forever, and at some point start failing. Flush, or using atomics to set a flag, can help in making sure that there's no reordering done by either the processor or the compiler or processor. In the training that I have in multi-thread programming, the whole concept of memory reordering and all the details take 1.5 hours. It's really tricky, really complicated. Most people never heard of it when they enter. Having said that, using flush everywhere is going to kill performance, because every flush means that all the caches are flushed out to memory, which may be a significant performance problem. So only use it when you need to. And then we have a few things that I deliberately want to highlight it in OpenMP 4. So OpenMP 4 was released, I believe, summer last year. And there are a few nice new things in there that I do want to talk about. But let's do a bit of politics first. Because there was a small company called NVIDIA, you know, right? They make graphics cards. And they at some point started making something called CUDA to actually be able to program those graphics cards and have some nice advanced parallel code execution on the graphics card. And then there was Uncle Sam, and he wanted a new supercomputer for his Department of Energy. And he said, I want an open protocol for that GPU offloading. So NVIDIA looked around and said, shoot, CUDA is not open. It's just us, and we don't allow any of our competition to use the same protocols. Realizing there were two other standards already, OpenCL, started by Apple, mostly active by Altera and AMD at the time. AMD is a good competitor of NVIDIA, so let's not. They are part of OpenCL, but no, let's not try to get everything in there and bank our future on it. Same for OpenMP. OpenMP 4 was already in the making. People were thinking about putting offloading in there. But NVIDIA needed the solution tomorrow, not when it's ready. So in the end, they decided not to go with OpenMP, to go for an even faster track. So they contacted a few compiler builders, started working on something called OpenACC, tried to keep it as close to OpenMP as possible, with the thought that if the need arises, we can migrate everything that we now quickly prototype in OpenACC into OpenMP. Well, that's where we are now. OpenACC is in its second revision. Works like a charm if and only if you have a compiler made by PGI, Cray, or CAPS. And the openness was threatened in last September when NVIDIA bought PGI. So at that point you have Cray and CAPS, and Cray and CAPS tend to work together anyway. So you essentially are stuck with two vendors providing a new standard. So at that point, NVIDIA started paying Mentor Graphics to actually put OpenACC in GCC to make sure that OpenACC remains an open standard. I would have preferred if they started paying Mentor Graphics to make OpenMP work with NVIDIA cards. Sorry, that's not happening right now. Why this exercise? Well, just to make sure to explain, OpenMP 4 does have target offload. You can say pragma OMP target to actually specify, okay, this code is not meant to run on my CPU, but offload it somewhere else. And somewhere in the future we'll have NVIDIA support for it. But this is what it looks like. Pragma OMP target, or if you have a large amount of code that you want to say all of this needs to go to the target, say Pragma OMP declare target, la 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 la, Pragma OMP end target. You can specifically say, okay, I need this data to go to the device. Or if you say, okay, later you can say, okay, update the contents of this struct in one or the other direction. Which tends to be a problem with GPU offloading anyway. Getting the code to run on the GPU probably takes you a day or two. Getting it to run efficiently, faster than on your CPU, probably takes you the rest of the year. Because you need to be really worrying about the amount of data, making sure the data is in time on the GPU and is in time back for your host to continue computations, which is painful.
What profiling tools can one use to track using advanced?
So NVIDIA obviously realized this very early on, so they made a profiler specifically to monitor what is happening on the GPU and how much data is going to and from the GPU. Featuring can do similar things. I'm not aware that any of the open source tools have that kind of tracking. I'm not aware of it, but it's a good suggestion. I'll check it. OpenMP has all those nice hash pragma OMP parallel, right? OpenCL starts with this amount of shitcode. And then I give up. Now, so conceptually, OpenCL and CUDA and OpenACC share a lot of common thought in that you take code, you offload it somewhere else, and you have to specify what that somewhere else is, and how you get the data over there, and how you get the code over there. The approach you take is very different. In OpenCL, for example, you take code, put it as ASCII in your binary, put a compiler in your binary, and have it at runtime actually compile the code and upload it, which is Git complex. That's why you need what you do for CUDA, it's similar, but it's better hidden, because in CUDA you compile to some kind of a bytecode which you hand to the graphics driver who will figure it out. Similar Harry, it does better hidden.
Sphere for two groups
Can you
Sphere, which is a big group for OpenCL. So you can have better things. You get like
Yes, you're right. Indeed, OpenCL has been fixing a few things to make it more competitive. So, stupid guys like me don't burn it in front of the large audience. OpenCL really works for very specific use cases, like CUDA works for very specific use cases. The beauty of OpenCL is that you can also offload to an FPGA. You can offload to a DSP, you can offload to a CPU, where CUDA can only offload to NVIDIA graphics cards. And I only have 5 minutes left, so I better start running. I don't think it surprises anyone if I say that this kind of offloading in OpenMP currently only works for one device, being the Intel Xeon Phi. Because Intel is really pushing OpenMP4 as the default programming model for Xeon Phi. So ICC, the Intel compiler, is currently the only one who has full support for targets. It's not present in client or GCC whatsoever, right now. Something else? Factorization, there we are. Factorization was left to the compiler up to OpenMP4. Only in OpenMP4 they now add yet another mechanism to specify factorization. We only have 4. So this is the 5th one. To actually say, okay, dear compiler, this loop should be possible to do with a factorized approach. So instead of doing one value at a time, take a big register, say to 56 bits, take 8 floats at a time, process them all at the same time, write them back. That's now also part of OpenMP. So you get things like pragma OMP parallel for SIMD, where you can say, okay, this for loop needs to be done in vector. And the beauty of OpenMP in that case is that you can also say, okay, I have this function that is also SIMD capable, but dear compiler, I'm not using this in a branch, which means that you don't have to write complicated code to only supply certain values in your vector. You know that all the values in your vector will be processed. Okay, let's check whether the Intel compiler actually makes sense of this. So I took a look at the assembly code. Yes, it does. And in a way that makes me wonder why Intel always shows this example. Because the return, so it's actually the minus minimum is indeed done with one single minimum of a packed set and one go. So yes, this is one big line of C code turned into one single assembly statement. The same for this nice RMS calculation. This subtract y from x, and then you multiply the result with itself. So somehow this is a really nice fit, and I wonder why Intel always takes this example to showcase. By the way, if you open up the assembly file, there will be 4 other versions as well. For example, if the last values do not fit exactly in your vector, so they have a special case for that, and they have a special case in case you're not running on the latest Intel chip. And I'm almost running out of time. More OpenMP 4 features that you shouldn't need in your first program. You can now tie a specific thread to a specific core, which is useful in some cases, but in reality it usually is overrated. Don't start using tying threads to cores if you can avoid it. It usually kills your performance. Same as for team, and I already explained what cancel cancellation points are. They are for early access. With 2 minutes left to go, pros and cons. I love OpenMP. It's easy, and like C, I can kill myself if I want to. It's very easy to shoot yourself in the foot because the compiler will not tell you if you forget something. It will happily create non-working code. If it works great. If it fails, you don't know. But it will run fast. Okay, thank you for listening.
We had a couple of questions already. We have time for one more question.
I can't answer that yet. Sorry. I don't know yet.
Next talk will start in 5 minutes.
Can die gasten ook? Nee, anders komt het goed.
Is dat leuk met die video?
Ja, redelijk, maar dat hier nog heel veel wat aan leren.
Ah ja, maar ja, dat
En ik denk dat dat niet echt durven aan de omdat ik...
Ze streamen dat live, hè, weet je dat?
Nee, ze streamen niet alles.
Dat streamen ze wel. Alles hier wordt gestreamd.
En dan dit
Naar heel de wereld. Streaming komt FOSDEM komt ook. Cool. En het werkt goed. No pressure en al.
Nee, maar
Is dat goed? Ik zou het overpakken, weet je.
soms, in het begin heb ik hem niet getoond, zo, en ik weet de slides van gezien.
Maar
Soms dat hij meer interactief was, dan kan ik er wel.
En dan zo altijd picture-in-picture gedaan. Slides en...
Ja.
Ja.
Maar niet, nee, al geweest slides toen niet. In het begin. Maar toen dat hij echt interactief was.
Ah ja, toen. Ja, dat is goed. Ik wil zien achter dat. Het is ook nieuw voor u.
There are my lectures.
Hi man, how you doing?
Slides. Hi, Andy. How are you?
I'm good, man. Hello.
I work doing the recording. I'm supposed to, yes. I'm not sure if it works. Yes. We're trying. So the room was quite small.
Hello. Hi. So you're recording all the talks? So it's
I don't know.
embarrassing.
It's supposed to be recorded. I'm just sitting here and I'm occasionally manipulating the camera. Just if you're speaking, don't walk around too much.
Number one.
Yeah, but if you're like down there, it shows you space.
Okay, so you expect to record speaker and
No, I can put the slides and the speaker in a little corner, but I need to design it for myself on the fly, and I don't understand really well how the
they gave you the amp.
Well, at first they said somebody would be here to do the stuff, and then it turned out it didn't. And then Ken tried to fetch the equipment, and then I went for a quick introduction to the main hall during the opening talks. But I don't really understand.
Now you're the AV guy.
Yeah, apparently. This will be excellent. I'm first going to fetch a sandwich because I'm
Oh. Was ich schon in der if you go down, we can just place sandwiches. What's the next thought? I have no idea.
Sound to the camera.
Excellent, thank you.
Do you know how to work it?
Yeah, so this side.
Okay.
That mic. Yep. It's actually quite loose. Yeah. Oh yeah, it's in Hebben we nog zo'n stekkerblok?
Okay, normally that should be working. I think that means you get the sound.
Like the guy who didn't get scanned, who didn't get had a background check. Yeah, one guy worked for the open around how they all lost, how they go again. I don't think I
My people, thank you very much.
I'll pause at 20 minutes, right?
So how much are I'll have to bring it. That's in chocolate, actually. So are we going to start?
You guys can do it. Yeah.
Yeah, sure. Or you can mute here or but here. Just put it against
I just see.
okay. much louder.
Ben, je crois, ouais. Si t'as le truc qui change ici, c'est bon. Hein. Tu vois, là, s'il y a ça, c'est bon. Hein.
Ouais, c'est bon.
Ok.
You can see the level is up. It's okay.